Hello, everyone. Welcome back to Calculus 2. So in this video, we are going to talk about 1.4, integration formulas and the net change theorem. So here's the objective. And then before I'm going to introduce the net change theorem, let's talk about the definition of derivative that you learn in Calculus 1. Basically, derivatives are amazing things, right? They have a limitless number of application, and one of the most important of application has to do with the rate of change. If you remember in Calculus 1, the definition of derivative of a function, that is a rate of change. For example, the derivative of position, right? If you take the derivative of the position function, let's say d over dt, you will get the velocity function by taking the differentiation. Do you guys remember that? Likewise, if you take the derivative of the velocity function, you will get the speed function. So let me take a look at this image. You're gonna take the derivative of the position function over the time. So position is changing over the time. I'm measuring the rate of change over the time. And then you got the velocity function. And then again, you're taking the derivative of the velocity function. You got the speed or acceleration function. So that was a really, amazing things about derivative, because it keep by taking derivative, you are able to get the velocity function, speed function, things like that. So that's the beauty of the differentiation, if you remember in Calculus 1. So that's the, kind of like graph of position, graph of velocity and acceleration that they show us the relationship, among the derivative. So what we're gonna do in 1.4, what if we are doing the backward, right? So what I'm saying is, let's say I already know the acceleration function, right? And then if I want to go back to the velocity function, what do you think? What do we have to do? You're going to just take the antiderivative. Basically, you're going to take the integral. So in other words, if you take the integral of the acceleration function or speed function, you will get back to the velocity function, isn't it? Because by taking derivative of the velocity function, you get the acceleration function. So we are doing the backward instead of doing the differentiation. So by taking antiderivative, in other words, by taking the integral, you're going back to the, the previous function. So one more time, if you're taking the integral of the velocity function, gotcha, you're going to go back to the position function. So in this chapter 1.4, we are looking at the relationship between, again, differentiation and integral in terms of the, one of the application, velocity, position, velocity, and acceleration. So take a look at it. I'm going to just make a little bit of notes here. You have a position function. And then this, whatever the position of the item is changing over the time. And then if you're taking the differentiation, you get the velocity function, taking d over dt, by taking the derivative, you got the next one is a speed. What I'm saying is you are going to take the integral of the speed function, you're going to get back the velocity function. Same thing, if you're taking the integral of the velocity function, what do you guys think? You will get back the position functions, because derivative and integral, they're so related to each other, right? So therefore, net change theorem exactly talking about this relationship. So whenever you have a function, right, if you're taking the integral, you will be able to find out either velocity or position function depending on what the given is. So if you have acceleration function and take the integral, you will get the velocity function's net change. And then you have a given velocity function, take the integral, you will get back the position function's net change. That's what we are going to do. So let's take a look at the example. I'm going to go to the example on the bottom slowly. So based on that concept, maybe we are able to solve this question. So let me read it. Given a velocity function. Ooh, so this is the velocity function as a given. So we know velocity is between position and speed function. So anyway, given a velocity function, 3t minus 5. So they are changing. The velocity is changing over the time for some particle in a motion. From that time t to 0 to t to 3, find the net displacement of the particle. So what they're saying, the net displacement means they're looking for the position function between 0 to 3. So step 1 is, what do you guys think? Let's find the position function. So we have a given velocity function. So if you're taking, right? If you're taking the integral of the velocity function, you will get the position function, correct? So that's what the relationship we literally talked about right there. If you take the integral of the velocity, you will get back the position function. So we're gonna set up that idea. So here we are going to take the integral. So therefore, we are looking for the position function, which is taking the integral of the velocity. And then the velocity function is a given, 3d minus 5. And then they say from 0 to 3. 0 to 3, we are looking for only between 0 and 3. So that's your, the range. So that's going to be at the end, when you finish taking the integral, you're going to subtract the large minus 0. Am I correct? So let's take the integral. Time to take the integral. So this is going to be, you're going to take the integral, so 3. So I can separate it. So 3, we have a t, there's invisible 1, adding 1 divided by 2. That's how you're taking the integral. And then 5 will be 5t from 0 to 3. And then I'm going to keep calculating. So this is a 3 over 2. T to the second minus 5t from 0 to 3. And now you're going to subtract from 3, that's 2. And then this is capital F of 3 minus the rest of them. Actually, that is going to be 0 anyway, right? So this is anyway 0, everything. So therefore, 3 over 2, 9 minus 15. So if you calculate it, this is going to be 27 over 2. And I can, change a 15, having the same common denominator. 30 over 2. So the negative 3 over 2 is the net change in this question between 0 to 3. So in this question, we need to understand how to find out the position function if you have a given velocity by taking the integral, right? This relationship is true. So therefore, all the information is given. So then you're going to finalize the answer. Okay, so that's what we are doing in 1.4. Pretty simple. So it's going to be a very short video. So let's take a look at a couple more examples. Are you guys ready? Ready? So here we go. I'm going to go to the next example. Let's go to the next example. Here we go. All right, example 2, water flow a tank at a rate of 500 minus 5t. So I don't know, there's a big water tank and then it's going to be filled, with the following function, 500 minus 5t. Over the time, they're going to be filled. Find the amount of water that flow out of the tank during the first 18 minutes. Okay, so I guess there's a water tank and then it's going to be filled over the time. And they want to know exactly the amount of the water, okay? So think about it. There's a water tank and then there's a function. I don't know, let's say we have 500 minus 5t. So over the time, as a t is changing, they're going to be filled quickly. And then they exactly want to know the amount of the water from 0 to 18 minutes. After 18 minutes, how much water will be filled? So think about it. We have a rate of change. This is a rate of change, one kind of like a velocity function, right? This is a velocity function. And then over the time, right, the position of the water is going to be changing. It's going to be filled. So what do you guys think? If you take the integral of that velocity function from 0 to 18, you can find out the position of the function of the water. In other words, this position implies that the amount of the water was here, and then it's getting filled. The position is going to be changing. So same thing, we are looking at the relationship. By taking the integral of the velocity, you will get back the position function. So I can set up this equation to find out the answer. Am I correct? So at the end, we're gonna do, right, capital letter of 18 minus f of 0, because we are looking for only between 0 to 18. So this is the net between 0 and 18. So the next step is simply we are going to take the integral. So 500 will be 500t. And then minus 5t invisible 1 plus 1 divided by 2 from 0 to 18. So what happened? It is going to be 500t minus 5 over t to the second from 0 to 18. Now I'm going to subtract from 18 minus 0. So 518 minus 5 over 2, 18 to the second power, minus the rest of them, it's going to be actually 0, because everything is going to be 0, right? So if you calculate this one, it's going to be a very simple number, 8190 liters per minute. So after 18 minutes, you will fill about 8,190 liters per minute. So that's your answer. Does it make sense to you? So this concept, you know, taking derivative and integral, it's really similar to each other. They're just, you know, opposite relationship and applied into so many, you know, application of problem set like this, or, you know, the moving position or filling out the water in many contexts. Okay, so we're gonna keep practicing a couple more, just a couple more, and then I'm gonna go to the next one. Let's take a look at this. I might not be finishing this question. I just want to give you guys the idea how to understand this question. Here we go. The rate of change of a population of insect, they keep growing with the following function. So the rate of change of the population of the insect. So this is not the position. They keep changing over the time. So this is going to be velocity function. And let me keep reading it. Find the net change of the number of the insect after 15 days. If the initial population is a 10 insect, how many are there after 15 days? So there is we know the position function, velocity, speed. So we are looking for the original population, the number of the insect, okay, after 15 days. And then here is the rate of change of the population. So this is the velocity function. Again, we are having the velocity function negative 3t second, 4t plus 1, and I'm looking for between 0 to 15 days. So if you're taking the integral with the velocity function, you will find out the number of the population of the insect. You know, over the time, the number of insect is changing, correct? It's getting increasing. I'm looking for only between 0 to 15. So this is the, you know, the equation that we can set up. However, don't forget this. There was an initial population. Initial, you have to edit. You have to edit initial number of the insect. Okay, so we are going back to the position function. So take the integral with the velocity function. from 0 to 15, adding 10, so that you will get the rest of the answer. So let's take a look at the integral. So step by step, let me just minimize a little bit. So if you take the integral negative 3 t to the third over 3, because I'm adding 1 divided by that 3, plus 4 t to the second over 2 plus t. 1 gonna be t, 4t gonna be, t second power divided by 2. So from 0 to 15, adding 10. Oh, everything will be simplified. Negative t to the third, 2t to the second plus t from 0 to 15, and plus 10. So this part, we know this is going to be f of 15 minus f of 0. Then you're going to adding 10, correct? So let me keep working. So let me go up here. So negative 15 to the third, 2 times 15 to the second, 15. This is a capital 15 minus everything is going to be 0 because you're going to plugging in 0 into everywhere. So that's all 0. At the end, you are adding 10 initial number. So let me calculate it. Actually, I haven't calculated that number. So you could go to decimal, or if you have a calculator. So take a look at minus 15 to the third plus 2 times 15 to the second plus 15, right? And then you should get some number, negative 2000, so negative 2019, 10 plus 10. So this is a little bit weird. We have a negative number. So I think we have a little bit of problem. So let me modify this question. Minus, instead of minus, well, let's change it to positive. Sorry about that. So if you change it positive, so everything is going to be just positive. And then let me just calculate again. So the number will be this number. So if you calculate this number, because it's not make sense that you have a negative number as a number of the insect. So we're going to have positive 3840 plus 10. That's better. So if you do the number between 0 to 15 days, you had a 3,850 number of the insect. And from here, they are keep increasing over the time. Does it make sense? So that I change a little bit of equation. Instead of negative, let's change to the positive so that it's going to be increasing. So I think this is the better answer. So the story is the same thing. You should know the relationship between position and velocity function, between integral and differentiation. So in this question, we are going back to the position function, so that we are taking the integral, not the derivative, taking the integral, and there was an initial number of the insects, so adding them, so that you had a 3,850 number of the insect between 0 to 15 days. And then from there, you'll keep increasing as the time goes on. All right. So that's good so far. So the next question, I want to give you guys a little bit of challenging time. Okay. So let's take a look at the next question. Here we go. Okay. So in this question, let's take a look at it one more time. If you remember, this is the position function. As time goes on, position is changing. And then if you take the derivative over the time, the next one is the rate of change, the velocity function. Taking the derivative one more time, you are getting back the speed function. Okay, so this is the derivative. Again, you can take the integral, right, of the acceleration function, then you will go back to the velocity. If you take the integral of the velocity function, you will go back to the position function. So this relationship is so understandable and makes sense to us. Now let's take a look at the question. If they're giving us the acceleration function, which is a negative 9.8 meter, is the acceleration of an object. What is the net change in velocity from 0 to 5? So they're looking for the velocity function and from 0 to 5. So hold on. Do we have any given velocity function? No. So to find the velocity function, what do you think? We are going to take the integral of the acceleration and you will get back the velocity. So take the velocity function will be take the integral of the velocity function. So this is so true, right? We talked about it. So there's a couple. Take the integral of the acceleration will be velocity. Take the integral of the velocity, you will get back the position function. So these are so makes sense to us. And then therefore, we have negative 9.8, that's the acceleration function. And then you are going to, if you take that, you will get the velocity function. And then this is from 0 to 5. That's it. We're going to work on this. So now negative 9.8 will be just negative 9.8t because that was a constant. You keep increasing one variable. So negative 9.8t from 0 to 9. So let me just minimize this part. So here, so that means capital letter of 9 minus 0. So what happened? Negative 9.8 times 9 minus 0. Right? This is capital 9, capital 0. So therefore, negative 49 meter per second square. This is the velocity function between 0 to 5. That's the answer. Let me double check. I think I have a little bit of typo from 0 to 5, not the 0 to 9. So this is a 0 to 5, so that I have to multiply 5. So if you calculate negative 9.8 times 5, so here it should be 5. I don't know where 9 came from, but it should be 5. So that's going to be negative 49 meter per second square. So this is the velocity from 0 to 5. All right, good. So now let's take a look at letter B. Okay, if the initial velocity was 30 meter per second square, what is the velocity at 5? So we already know what is the velocity at 5, which is this one. That's from 0 to 5. So we have to add in just the initial velocity. So initial velocity from 0 to 5 of the velocity function. So this is 30. We already know this is negative 49. So it's going to be negative 19 meter per second square. So this is the second question answer. You can think about it. Are you getting better? Does it make sense to you? So take a look at it. Think about it. It's going to be fine. So I'm going to do slowly and surely. Let's take a look at one more example, the last one. All right, so we are keep taking the integral to find out the before previous function. So let's look at this. So evaluate the definite integral of at function, negative 5 sine x over the interval, negative pi to pi. So what is this? So first of all, I want to take a look at negative 5 sine x function. What does it look like? And then between negative pi to pi. So first of all, we know the sine x function. If you remember the sine x function, we have the same pattern. So the height is 1, the minimum is negative 1. So every 2 pi, we have the same function, correct? And then if I have 5 times the sine x, you are just increasing, you're going to stretch this sine function higher, 5 up to negative 5. So the higher is a positive 5, and then it's going to be negative 5. But the pattern, every 2 pi, you will get the same pattern up and down. But now what we are going to do, we have a negative 5. So we are going to be reverse it. So -5 sine x, you have to move back and forth. So the up now is going to be in the bottom. Up is going to be up. So this is going to be -5 sine x, pattern every 2 pi. So we used to go to up and down, but now since of the negative, it's going to begin negative and up, negative and up, negative and up. And they want to find out the kind of like area, right? Because they were looking for the integral, help us to find out the area between -pi to pi. So this question, simply we are taking the integral from -pi to pi of the following -5 sine x function. By the way, this pattern is going to be like keep on going, right? And then -pi is going to be here, positive pi here. They're looking for this area. So how would you be able to set up that equation? We are going to take the integral from -pi to pi. The function is -5 sine x, and you are taking the integral with respect to x variable. So that is going to be capital pi minus capital -pi. So that's going to be, this area, correct? So we are going to take the integral. I'm going to bring -5 to the front. So -pi sine x dx. So somebody, maybe you can go to the integral table. Do you remember? What is the integral sine x? It is going to be negative cosine x. Go back. Because although, outcome is a given, if you go to our module, there's an integral table. So by taking this, you have a -5 to the front, and then that is a negative cosine x from -pi to pi. There we go. And then I can continue. This double negative changed to positive. So +5 cosine x from -pi to pi. So simply you're going to work on, right? Capital pi minus capital -pi. So 5 times cosine +pi minus 5 cosine -pi. So you can go to decimal. Cosine pi is a -1. Cosine -pi is also a -1. So it's going to be -5, double negative change positive. Yep, it's a 0, which makes sense. One is a positive, negative. It's a symmetry. The net area will be 0 because this is a symmetry range. So here we can take a look at how, integral can be applied in many different contexts, to find out the position, velocity, acceleration, and also area, so that you can find out, the benefit of using integral in many, many applicational problems. So that's all about it. 1.4 is a very, very short topic. So after watching after watching this video, definitely you can complete the question quiz 1.4. Feel free to join, our discussion chapter 1. If you have any question, that's where you are engaging with other people, helping to each other. And then definitely that's your participation points. Okay, so I will stop here. I will see you guys in the next video. See you soon. Bye-bye.